This presentation is brought to you by the Ateneo Innovation Center. 1%. That's just about the ratio of people who experience venous leg ulcers. Yes, this may seem to be small, but ineffective compression therapy can lead to huge figures. In US alone, this translates to 600,000 patients, 2 million working days wasted, and 5 billion unnecessary healthcare costs. People have been combating these for a long time now, but what if I tell you that this sort of problem has not been resolved yet? At least not until recently. Well, a research team led by Matthias Cole from the Massachusetts Institute of Technology was able to create vibrantly colored stitchable fibers able to traverse the entire visible spectrum depending on the pressure applied to it. Here's a sample of how it works. Each strand of fiber is made of a multi-layered cladding composed of spin-coated polydimethylsiloxane and polystyrene polyisoprene choy-block copolymer to create elastomeric photonic fibers acting as a Bragg reflector. As a sensor, one of its most important aspects should be consistency, and the first two figures show that points at comparable levels of strain tend to cluster together. In fact, the reflection peak only shifted by 3 to 5 nanometers after 10,000 cycles of stretch and relaxation. For the sensing applications of interest, they calculated the color trajectories of model fibers in the CIE color space to predict their color response. The last figure shows that the fiber transition is observed to be from blue to green via violet, red, orange, and yellow, but given the capacity to control the cladding and coarse composition and structure independently during manufacture, it is possible to design a wide variety of tailored color responses for specific strain levels. Now, going back to the research team's focus on compression therapy, the controlled pressure gradient during these treatments are crucial to avoid further injury and longer healing time of the tissues. This seems to be a simple addition to the system, but by correlating the true strain experienced by the bandage to the natural change in color of the fiber sensor, they were able to provide a quick, more accurate, and real-time depiction of the pressure. Moving on, a patent already exists for optical fibers in general since 2009. In this patent, there is a claim on optical fibers utilized as a sensor for measuring a parameter of interest, such as temperature, strain, photonic energy intensity, electric field intensity, and magnetic field intensity. More recently, there is also a pending patent under Matthias Cole's name, whereby a tunable bandgap multi-layered fiber related to the subject of this video is included. Despite all these, the fibers have yet to be seen in the market, but they are already bridging towards partnering with athletic apparel companies to study how the fibers can be woven to create new fabric and new designs. Other than fashion, if we go back to the big picture, there are lots of things in our world related to knowing the stress that should concern all of us, like infrastructure stability. Furthermore, billions of people are into fitness and medical rehabilitation. So if say we integrate these fibers to a color mapping application and recalibrate it, we can create the first digital real-time strain-to-color mapping application with lots of potential. Given this, a person can now do her fitness exercises at home and send the strain-to-color data to her trainer or doctor for ease of analysis. A major improvement in remote telerehab. Speaking of improvements, the fiber material can also be incorporated to other recent technologies, such as the Myo armband, which detects muscle firing and fatigue, or different cooling technologies to reduce inflammation in many diseases like chronic venous ulceration, post-surgical hematoma, burn-related wounds, and other maladies. Who could have thought that a thread-like material can provide more time, less spending, and greater security? This ends my presentation. I am Vincent Tumaneng, and this is about color-changing fiber sensors.